looked at the schedule. So
by mistake,
problem.
I announced a wrong time.
Yeah.
So I have started going live now, Professor. We request you to please start your lecture. Thank you so very much.
So welcome to this. It's sometimes called tutorial, but I continue my way of showing results, and it's a kind of lesson or lecture. So to be sure that I don't miss the MATLAB part, I will start with that. So let me then share my screen related to MATLAB, and I think it's best if I take my whole desktop then too, because there are a number of screens. So then I hope you can see my my whole screen, or?
Yes, yeah.
Okay, good. So my idea is to show you a couple of basic functions, not so many, but one on reachability, which is very short, and that also means that I think it could be quite easy to follow and understand. One on this reinforcement learning, the Q function, and one on synchronization, and also I will add one on the abstraction part, which I will talk about this evening. And for all of these functions, I have a test function above. So that means that, say, for instance, for this reach function, I will deliver this function, which means that you can just write test reach without any parameter, if you like. Then I put just a standard value here. And then I call this reach function for a number of different inputs. It's partly my way also testing that the algorithm works correctly, and also some performance here of the algorithm. And the first ones are very small models with maybe I should try to explain the data structure here a little bit, because I'm working with two types of representations of automata. One is based on, you could say, the delta function. And then the delta function tells first n delta, how many transitions are there. And the delta here is going from, in this case, from an initial state to a next state 2 and another next state 3. I think I have some more detail. I will actually give you the code where I generate the delta and the transition relations. So based on that, you will also be able to understand a bit more how that data structure is built. Because here you have also the events involved here. But it's not totally obvious based on what we see here. So you see that the reach function has the delta as input, and then I just check the reachable states, okay, in this case it should be from 1 to 10, and if R generates that, then you also get the 0 element of that case, test case. So for instance, if I run now, okay, window, let's see. Yeah. So for instance, if I run this test reach, you see that I get some answers here, and they are related to the size of some examples in the end, where I think in both cases I try to generate a synchronization of two models to blow up a little bit more. And you see that all of these still generate a correct answer, because the E vector here should generate 0 to be sure that they are correct. And there are also some elapsed time here for the execution times. So in the same way, I can also test the sync function. And yeah, there I have also added, I haven't moved that away. It's a profile function, which is where you can see a little bit on how different functions, how much of the time they are used. Actually, maybe I could keep this, because if you're not familiar with this, it is quite a nice feature to have if you're testing when you're testing your code. And then also for the Q function, I have a test for that, but I would say that I think that this element here, it's a number of iterations in the Q function, and okay, that I have in another directory. So the Q function there, I don't have so much of tests and so on. So but there is at least one umbrella function over the specific code. But let's look a little bit more on the function itself. So this is built on the idea that you build the set of reachable functions, and then the delta of R is those that are new, that has not been reached before. So from the beginning, I say that R is, here the input is that I is this set of initial states. And then I introduce that as a set. And then I say that the first delta is equal to this set. And then I try to update this set, and then I say in the loop here, a fixed point, that okay, the old delta is the current delta, and then I say that the new delta is just a vector element with one element. With yeah, okay, what is once? It's okay, it's just it's actually an empty matrix, but to get some things working correctly here, but it has still a vector with empty elements in. Okay, so for all the states in the old delta, I iterate on this delta R, and then the delta, small delta, the original delta function is iterated, and that adds new states. And you continue that for all the states in delta R, in the old delta R. And then you take the difference between the new delta R and the current total set of states. And in that way, you get exactly the new additional states. So from the current delta R, you go forward, but then it could mean that you also recognize some old states that you have already seen before. So by this set difference, you only take the real new states, and then you add this to the R function, and then if this delta R has length 0, then it means that you haven't added any more states, and then it's a sorting, and then you can return here. Yeah, I think this is actually the most simple one. I have also implemented some other versions which are a bit more efficient, but this is definitely the most simple implementation of this. But it has to do with we have to understand the delta function, and yeah, maybe I should try to see if I can find that. That should be there. If I take the transition from transition relations. Trans to, shouldn't it be that? Delta to trans, trans to delta I'm looking for. There it was. Okay. So here, if you have a transition relation, and that is easy from a data point of view, because it includes on every row a transition relation. So the first row has 3 elements: source state, event, target state. And then you can, if we look at this from the forward point of view, it's easiest. So then you go through all the transition relations in this T. It means that we take the length of the first column in T. Okay, I'm just looking here and see if there are if events. It's just some initialization here. Okay. So then I say that I source, if I go forward, it's 1 and target is 3. So as I said, the first element on every row is the source state, and the third element is the target state. So then I say that Q is, for every transition, is the I source. So it means forward that it's I, 1. Okay. Then N delta is actually answer how many states do you have in the how many target states do you have for the state Q. So N delta is just a row vector, or a vector where you add, if you add 1 element, you also say that, okay, now the number of states from Q is 1 more. And then the delta function, in this case, it's now you would like to add 1 element, and then you take the last, say that N delta is now 3. It means that you have 3 target states, and then delta on the third row, and state Q is then the target state on this. So yeah, I should have something to write down here, but the row n delta just tells how many target states you have for each source state, and the delta function has then on in each column it generates the target states. So for instance, in the first column, from the which states do you have from the first source state? Say that it's state 2 and 3 that are the target states from state 1, and then this delta will get in its first position, say 2, because that is one target state, and on the next row you will get 3, which was the other target state. So you just fill the columns of the delta function with the target states of a specific source state Q. And if you also need the events together with the target state in this which you generate in delta, sigma delta generates the corresponding event to that target state. So that's why you take ti of comma 2, because comma 2 is the place where you have the event. So if you look at this trans to delta and delta to trans, then you definitely should be able to understand the data structure of this function. And in the reach case, I was a bit confused here because I was looking for the events. But the thing is that I don't need the events in the reach function. I only look at from each source state, I look for the target states. And those are then obtained by adding the delta of to 1 comma n delta of q. That means the number of rows you have for state q, the column q, and those are added to the current delta r. So I hope that will be clear. And then once again, you have the test reach with a lot of these functions. So for instance, we could then explain once again, let's say this one. This means now that you have one target state for state 1, one target state for state 2, and one target state for state 3. And the target states are, for the first state, you are going to state 2, and for the second state, you are going to state 3. So that means the sequence, you're going from 1 to state 2 to state 3, but you also have a self loop in state 3. So from state 3, you're going back to state 3. And for that, you can also generate the reachability. And of course, in this case, it will the reachable states are simply 1, 2, and 3. Okay, so then we go for the sync function. Actually, that is significantly larger, but it's based on, it's also based on this delta functions. And then you have then you need also the events. You have the number of states, the events, and the delta function. Okay, here n delta is first the number of target states, and here delta you have the actual target states, and in sigma delta 1 you have the corresponding events, and then comes the initial states. And if you have any state labels, and then you continue. So it's quite many elements in this synchronous composition, and then comes corresponding for the second automaton. And then in the end, you also generate number of states, the alphabet, the number of target states, and these list of these target states, and the corresponding events and the initial and lambda functions. So this is the whole. You see here that I made a test of this in Jerusalem, the 7th of July, 3 years ago. I was there on a conference. So sync returns the synchronous composition of two automata. And then what I do in the beginning here is to generate the different divisions of or separations of the shared alphabet, the events in the shared that are shared. First, the sigma is the union of sigma 1 and sigma 2, and the shared events are the set difference of the intersection of the it takes this intersection of the first and the second alphabet. So this is just the definitions of the alphabets. And then to this I also add if there are any specific no, okay, sorry, I take away the tau and epsilon events from this. Then instead I add those to the now I'm a bit uncertain here. Sigma S. Okay, I assume that there could be tau and sigma in sigma 1 and sigma 2, and then they are still in the local alphabets. Yes. So here I only take the shared events, and they should not include the tau and epsilon. Yeah, and here are some specific more. Yeah, this is, you could say, a more of a logical description of this information. And it's just because I try to code this with some logical integers or logical vectors, I would rather say. So yes, this is a little bit tricky, but it's written in a way trying to make it as efficient as possible. So the long loop here, or the big loop here, is that we go through first for the shared events, and then the local events in the first, and then the local events in the second one. And there are also some display function here that can be added to see what happens. And then the update also the lambda function, and then some cleanup in the end here. And yeah, I mean, this is one way to make the synchronous composition, and I believe this, at least in MATLAB, is the most efficient way to do it. Then for the Q function, you see that there are a lot of input parameters here, and they are depending on what kind of added features one would like to have here. But for instance, one is of course this how much of this epsilon grid, that should be a parameter for that, number of iterations, assuming that you start with some initial state. Of course, we also, since this is a simulation, we also have in the simulation we need to have the delta function, and what is the result of this is that we generate the Q function. So, but in the Q function, we trust on the simulations of the delta function. So here, going through the iteration here, we can say that there are some details here which I leave to yourself to evaluate. Actually, I don't remember exactly why I did all these things, but at least you can see here that there are some epsilon greedy stuff. This PQM, it's obviously related to the random generation here. But as you see here in the end, there is an update of this alpha, and alpha is actually a function which includes a number of possible updates of the learning factor. It can be 1 over k, but it could be a couple of other versions, log k divided by k, or for instance, if I remember correctly, and some others. So, but there are not so many additional functions. Actually, I think it's only this alpha, but also we can take a look at that machine learning. Let's see, is it like I have there? No. Where is the alpha function? Okay, I don't understand really why these are in gray, but here you see the alpha function. And for some reason, I don't know why I cannot open it. Let's see if I go outside here. Here you see, for instance, these different, it was log k divided by k, which was one update, and the most simple one is the 1 over k. So it's just that you have to take one of these and to see how this influences your result. Then this PQM. Okay, it looks like PQM is a built-in MATLAB function. Let's see. Yeah. Or? No. No, okay, sorry. PQM here is an input. So it's that is then something that should be generated in test queue. So in this case, I have as a simple example, I have a given transition function. And okay, I have obviously another function here also, trans to delta, including these PQM. Let's see if we can open that too. Yeah, and here there are obviously some added features related to that, but I think I have to leave that for yourself to. Let's see. Okay, next state returns the next state function delta forward or backward, including cumulative probability for probabilistic transitions with the same action. Okay, so it has obviously to do with the probability transitions. So by that, I'm sorry. I mean, this my plan was not to go through to explain all the details here, but I mean, this is something you can just take for as it is and play around with as much as you like. And I will move these out to a zip file, so I'm sure that it can work with without any additional functions. So you get all of the subroutines, you know, all the additional M functions, but they're not so many, okay, then I will spend the last 45 minutes on these reduction principles, which I talked about quite much earlier, and I indicated them a little bit in the also in the timed optimization, because there I also had the possibility to join some states, and actually the paper I tried to finalize, we got an extended deadline until Sunday night now. There I will also try to relate that reduction, which I show there, to bisimulation, which in itself could be of interest. So let me try to explain a little bit of what reduction could mean here. If we take this simple automata model, then you see that, okay, you can make an A, a non-deterministic A actually, meaning that you reach until state 2 and 3. And after that, you have a B or a C, but you return with the same D from both these states. That means that if we should join 4 and 5, we should still get the same future behavior. Because in both cases, with the D event, you reach state 1. That means that we say that these two states, they are bisimilar. They can be joined into one block state, and that means that we now have introduced a reduction, which means that you generate a partitioning of your state space. In this case, one element is 1, 2, and 3, but the fourth element includes both 4 and 5. This state partitioning is also called equivalence class, or that, let's say that the elements here are equivalence classes. So states 4 and 5, we say that they are equivalent. Of course, the question based on what? Why are they equivalent? And in the basic understanding is that, yes, they have the same future behavior. Then the question, how can we determine that by a kind of algorithm? And then if we look at what I called a block transition relation, what do I mean by that? Well, if I look here, yeah, we can say now, assume that I have achieved this. No, okay, I should start with this. Here I have a transition from 1 to 2 with an event A, and that means that I describe this as a transition from 1 via the event to state 2. Now I still consider these generally as blocks of states, because after some time we will get state blocks here. Then you also have another transition from 1 to 3 with an A. So this T pi R1 is simply block transitions. Which are the possible block transitions from state 1 in this case? Which are the block transitions from state 2 then? Well, with this partitioning we have generated here, then from state 2 or from state block 2, you have a transition via the event B to this block state 4, 5. And from state 3, you also have a block transition from state 3 via the event B to 4 and 5. Okay, now we come to the critical question, why could I join 4 and 5? Simply because 4 and 5 have the same block transition, namely that from 4 and 5 you can via the event not B, sorry, it should be D here. I can go back to state 1. And from the beginning you start with these these states here. And then actually the assumption is that your block, your partitioning includes all states here. You just have one big state here. And based on that, we ask ourselves, what kind of division do we need to do here to still preserve that the block transition are the same? And after one iteration here, we can see that 4 and 5, they will have the same transition because 4 and 5 are the same block, and you have the same future, namely state 1, and the same label B. So this is once again a fixed point iteration. And the formal definition of this bisimulation partition is that, okay, your partition should, for every state X, should be such that the block transition for state X is the same as the block transition for state Y. At the same time as if you have any state labels, they should be immediately separated. So if, for instance, if we should have a state label, say P for state 4 and 5 for state, P and Q for state 5, then these two states cannot be joined. And then the result will be that there is no reduction on this. If I had different state labels in these two states, I will only get this model back when I try to minimize this. But in some other cases, I mean, here I could only reduce this to joining 4 and 5, but in other cases, of course, we can do much more than this. But the technique here is in the algorithm is to look at the block transitions and see that they should be the same. If they are the same, then you have then they belong to the same partition. And the block transition is then defined as pi of X via an event A goes to pi of X prime. And this is possible if there also is a basic transition from X to X prime. and that there is a block state with this within this with this partitioning, and here I have an example where I have a block state 4, 5. I have a transition to another block state, which is a single block state. So if you see block state B to another block state, it generates this, but with the pre-assumption that for every x here and x prime, you have also a transition in the original system. So for instance, from 4 and 5, there should be a transition to state 1. And it is from both 4 and from 5. This is a little bit tricky to understand, but when you have learned the procedure, it's actually quite easy to apply. So I think I will not go through too much of okay, it's one more slide here on the basic algorithm. This is a bit more complicated example, but we can see here that state 4 and 5, they have the same future behavior because it's a self loop with an E to itself, and they have the same state label psi. And also this state 7 has the same event self loop E and the same state label psi. So actually 4, 5, and 7, they have the same future, so they could be joined into this 4, 5, and 7 with the state label psi and the self loop back again. In the same way, 6, 8, and 9 can be joined since they have a self loop with another event f, but the same state label. So 6, 8, and 9 can also be joined. And now it's interesting that, of course, this is a constructed example, that these states 6, 8, and 9, the transition to those target states have the same event D, and the source states for those transitions also have the same state label. So based on this, it's actually possible to join even state 2 and 3, at least to go via D to this. But since also these states 4, 5, and 7 have the same event going to these target states, in both cases from state 2 and 3. So that means that 2 and 3 can be joined, and out from this you have a C or a D. And then from the first state, we also find that we have the same state label in both 1, 2, and 3. That's not necessary. We could have another state label here. We could even say put the empty state label here. But we can go to a state with the same future. You have the same future in state 2 and in state 3, namely that you can take a C or a D action. And if you take the C, you will get a self loop E with state label psi, and with the D, you will get a self loop with F and with the state label psi instead, or Xi instead. So in this case, it's constructed example, but it shows that the basic bisimulation could, in this case, reduce this system quite significantly. And if you apply the algorithm also to this, you find that the block transitions for 4, 5, and 7 are the same. They are that you have a block 4, 5, 7, E to 4, 5, 7, and self loop. And this is valid for both when you start in state 6, 8, and 9 for the F transition, and when you start in 4, 5, and 7 for the E transition. So that means that we confirm that these can be joined. And then the question, why can we also join 2 and 3? Well, because they also have the same block transition. From actually here we have a set of block transitions. One with 2,3 via C to 4, 5, 7, and one with 2,3 with a D to 6, 8, 9. But the thing is that both state 2 and 3 have the same 2 alternatives. So both alternatives are included in both 2 and 3. And that's why you can join them. And in the transition, the block transition for 1 is simply 1 to 2,3 with an A. And yeah, I mean, here it doesn't matter. Since it's not joined with anything else, it's no more state that have the same block transition as state 1. So this doesn't matter, so to say, what is stated here. It's unique. But by this, we can actually join state 4, 5, 7, 6, 8, 9, and 2 and 3. And it was also interesting that we started already from the beginning with this partitioning 1, 2, 3, 4, 5, 7, 6, 8, 9, based on the state labeling, only the state labeling. And that's why that partition is called P lambda, where lambda is the state label function. Well, in practice, this type of restriction does not give that much. But now I will come with something which is much, much more powerful. And here I've contributed a little bit myself, also trying to join 2 types of bisimulations. Actually, once again, we could find a few publications, old ones, which no one mentioned, but our concept was actually published by 2 or 3 papers 10 or 15 years old. But what I've contributed with is that all of these bisimulations are expressed in this way, which has not been explicitly said before, which is actually quite interesting, because it is in itself an interesting algorithm, and it's also actually quite a good algorithm. The algorithm in itself was published before. It was formulated a little bit different, but they didn't realize that, oh, we could even have this as a definition of the bisimulation itself. Actually, bisimulation is from the beginning always formulated as a relation, not as an equivalence. And then they need to prove that it's an equivalence. And some of these equivalence proofs are extremely complicated, especially for this branching bisimulation. And I can tell you that I've spent nearly half a year on just trying to prove the relation between the original formulation of branching bisimulation and my formulation of branching bisimulation. And now I think I've done that, but that was horrible. And partly because the original equivalence proof is so complicated. Now I will at least show you by examples how this branching bisimulation works, and it's once again much more interesting. If I have a model with some local events not shared with any other subsystems, and the local events can then be replaced by what we call hidden event tau, which explicitly say that, okay, no connection to anything else. You can even, sometimes people say that it's unobservable, but in my view, that's not correct. It's hidden. It's hidden. That means that, I mean, if I am in state 1, 2, or 3, what does it matter? No. I mean, from an external point of view, it's enough that I say, I know that, well, the system is in state 1, 2, or 3, and I can join them. And then when the visible, so sometimes this is also called not hidden, but also invisible. Then with the visible action, I move to another state. So here you see that by just these simple notion or observation that these are hidden or invisible, I can immediately join 1, 2, and 3. This is called branching bisimulation. And it was formulated by a quite well-known person within what is called process algebra. His name is Glavek, and he has been in Australia for many years. He was first acting in also at Stanford. I met him in Sydney a couple of years ago, and I was interested to hear what he thought about my ideas on this. And yes, after some discussions, he realized that my formulation was quite interesting. And his feedback was that, well, but you should prove that these formulations are equivalent, that they are the same, because the original definition is completely different. And that was what I, in the end, had to spend at least half a year to fix. But now it's done. I haven't published the paper yet, but it will come. Kripke structure, that is an alternative, which also is captured by my formulation here. And that means that I can also then work with state labels instead of transition labels. So in this case, I have the same state label in the first 3 states and a different one in the 4th state. And by this, I say immediately, why not join all these 3 states in one block state? Because you could say that in the Kripke structure, there are no event labels or action labels. It means actually that all of these transitions have tau labels. Nothing is visible except for the state labels. And when you have the same state label, they can also be joined into one state. Now it could happen that is you need to make further, so to say, changes here. Or further partitioning, we can say. Let's take this example, which now has both state labels and transition labels, and some of the transition labels are tau. Then we see here that you have a tau and you have this between 1 and 2, and they have the same state label, so they can be joined. Then comes a visible A, which means that must still be preserved in the abstracted model. But 2 and 3 and 4 can also be joined because they have the same state label. Why not join this up to 7? Because they have the tau in between all the way, invisible tau transitions. But here you see that 7, 6, and 5, they have different state labels. So there are 2 restrictions. You must have the same state label and tau transitions in between. And that means that 7, 6, and 5 can be joined, and 3 and 4 can be joined. And then you have the visible B to the final state A here. So you could say that these examples illustrate more or less what can be done, but there are some additional aspects here to be considered. I think I will, yeah, okay, we can say that I introduce here a notation that, okay, if I have a sequence of tau events with the same state label, followed by a visible event to another state. This can be expressed in this way, where the pi here says that you have the same state label or even they belong to the same partition. And this is what I call here a stuttering visible transition. And if A is not equal tau, or if you don't have the same, or if xn and x prime does not belong to the same state partitioning, then this is something that cannot be joined. It's what we then call a visible state. So mean that the first n transition are invisible, while the last one is visible, either because it's a visible event or because you move from one block to another block, state block. But apart from this, it's interesting that the branching bisimulation is now expressed exactly in the same way as the original, much tougher bisimulation, where they don't care about the tau events, that they are considered to be visible in the same way as all other events. So this is actually the same, and the computational algorithm is based on the same type of algorithm. But there is one difference, and that is that the block transition, they are defined in a slightly different way. Namely, instead of having an ordinary transition here, x transition A to x prime, we have this extended stuttering visible transition. And this magical difference or change immediately gives us the branching bisimulation. Okay, in this case, we could also confirm that these block transitions within this case block with an A transition from 1, 2 to 3, 4 is the same for 1 and 2, and for 3, 4 you have the same transition to another block, including 5, 6, 7. In this case, because they have different state labels, although they have a tau transition in between. So it's the tau. Sometimes you cannot get away from the tau transitions. You still need to have. It's not only that you can trust that all events should be visible. There could be some invisible tau transitions, but then it's mainly because you have different state labels. Okay, from the last one, it's just that you have a self loop here. And this meant that we got this model in the end, yeah, okay. Here is another example, and let's see, what time is it? Yeah, okay. We have not so much more time here, but I will continue at least a little bit more. Let's see. Okay, yeah. I try to make this quite quick. In this case, we have two transitions here with visible events. But assume now that A and C and D are local events. That means that we can immediately here see that we can join state 1 and 2. They have the same state label. And then we get the visible B. And then it's interesting that you get also a loop here with a tau event. But the same state label, so it's joined like this. And then from this P state label to the Q state labels, you have a possibility to join 5, 6, and then you have a visible E event back. So this is the Bronsted bisimulation reduction or abstraction from this original model, where we have identified some local events. So quite many tau events we have in this, and then we can reduce that from 6 states to 3 states. And now we come with a really interesting thing, and that was something my colleagues, this is not my invention, but it's some of my colleagues who introduced this concept. Well, actually, yeah, okay, it was formulated by also some other people, but it was once again this typical situation that it was invented by my colleagues, but then especially myself, I found some old references which formulate exactly the same. But my colleagues, they added some additional features which was not published before. And this is really something great. And it was also the idea I had yesterday when I talked about the timed optimization. And that is that I identify local events in every of these models. And then I try to abstract the individual models before I make any synchronization. And then I synchronize, say, model G1 and G2. And then maybe I get some more local events that are only involved in, they are shared between 1 and 2, but not with the rest of them. It means that when I synchronize 1 and 2, I get more tau events, and I can make further reduction, further abstraction. And then you can continue in any order between these different models and synchronize more and more and abstract more and more. And in the end, quite often you get extremely small model. Let me illustrate that. Here we have an example with a sequence of events and one final marked states, the same for the second, but they have different state or transition labels. If you synchronize this, you get n square states. On the other hand, if we now say that, well, okay, all these events, they are actually local. There are no shared events at all. So we can replace all these with tau. And we also say that all the first labels, except the last one, we put a P label on. Because here I use this fact that the most common assumption that you should take the union of state labels. And if you do that, and then you can first abstract this model just to 2 states. All the ones except the last one can be joined because they have the same state label, both for the first and second one. And then we come with this role that, okay, to join the different states here, to synchronize these two, what kind of, you will get 4 states, as we see here, but what will the state labels be? It will be the same in the first 1, 1 and 1, 2 to 1, but not in the 2, 2 state. Then you will not have any state label, because here we're taking a union between them. So for instance, 1, 2, then you have only state label P in state 1 in the second, not in the first model with state 2. But now we come to the situation where we can see here that, well, all these three have the same state label. And actually, we can also join all these three. So the final result is here with one additional abstraction that you only get this model. We get a reduction from n squared to 2 states. And we can find that, okay, fine, the system is non-blocking. It's possible to reach the final state, the marked state, which is state 4 in this case. I will not make any more comments on this. Here is another, a little bit more interesting example where I have resources, I have buffers. The resources only have 2 state labels. The buffers could have an arbitrary number of places, say m. And in the end, I also add an additional specification of a type saying that, well, I would like to make an AN followed by a BN. And if you remember very early in the course, I said that, okay, if I introduce this type of specification, and if I don't include the alternative CN in the alphabet of this specification, then we will get a deadlock. And that is exactly what will happen. Let's see. Then I can make an abstraction of the buffer and continue the buffers and continue. And in the end, I will get this model as the final abstraction. And actually, yeah, let's say that this is the absolutely final abstraction. And it's interesting. It includes 3 states. One where you can loop around without any problems. You mostly have P states. But there is a possibility that you reach state 2 here, which is a deadlock state. And this was exactly what I was looking for. Is there a possibility that this total system is a deadlock, is non-blocking? And that I confirm by this extremely simple model. And based on the state labels I have here, I can ask for any temporal logic expression, reachable, eventually, always, etc. And if any property is satisfied for this abstracted model, it's also satisfied for the original model, which is quite a fantastic result. The only thing I cannot do is to use the next operator in temporal logic. That does not work, but all the rest. Here is also finally a comment that I can make a reduction on even Petrinets in a very powerful way. Actually, every place here can be represented as a buffer. And since then, I have a number of buffers coming after each other. And that was more or less what I showed in the example before. It's possible to reduce this to actually only one place with the sum of the restrictions. This place is restricted, bounded to only include a capacity of M1, capacity M2, capacity Mn. This can be reduced to a Petrinet with only one place, but with capacity M1 plus M2 until Mn. And this means that I have achieved a reduction in state space of, in principle, M to the power of n, down to nm states. So it's an extreme reduction in this case. Now, for my students, I told them that, okay, it's a bit hard to learn all these things I've told you. But if you learn only one thing, that you can join sequential states with the tau in between and the same state label. So a tau transition can be deleted when no alternative transitions are involved in the source state and the source and the source and target states have the same state label. PP, for instance, in this case. So with this extremely simple rule, you can still achieve a lot of reductions. So although I gave them this in the last lesson and I explained more or less in detail what they should do, I gave this as an exam. And in this case, you see that you have two local events in the first one, A1, A2, one shared with the second one, B1, and the shared between G2 and G3 is C1, and C1 and D is shared between G4 and G3 and G2 actually. C1 is shared between all three, but D is only shared between G3 and G4. Now, this is solved, the reduction of this, which includes altogether, my guess is 3, maybe 3, 9, yeah, up to 20 states or something. And after the reduction, I can once again move this down to 3 states. And I mean, if I look at this, can I say that I have deadlocks in this system? I cannot see that immediately, at least. But here you see also, once again, you have a blocking state here. And with this reduction I mentioned, I can immediately say that G1 only has a self-loop with B1 because A1 and A2 are tau events and they can be skipped. So it's just loop around with B1. And for B2, I also have, well, not a self-loop, but when I've synchronized, I can at least skip B2. So I have B1 going back with C1, and that's G2. And then I synchronize G1 and G2. And then I can actually skip the B1 transition because then I get the tau for that. And in the end, with an additional abstraction after the synchronization, I only get the self-loop with the C1. Then I can join G12 with an abstraction of G3, and I get this model. I cannot exclude C1 and D because they are also included in G4. When you synchronize these G13 and G4, you get this. And now we have the final abstraction where I can also skip C1 and D and replace them with tau. And then we get no more reduction than this. So actually this is the same as this one, but it's only that since I go for abstractions here, I also hide all the events. So in the end, we don't have any shared events. So that means that all events are tau, but there are still some state labels preserved. So we have a behavior here where we can go from no state level to state level P, move around, but unfortunately it's a risk that we can also move to a state which is blocking with still a P state. So yes, this was all, and I hope that you at least could get a feeling that this is quite fantastic tool to use for abstraction. It does not help you in all situations, but it's possible to use both for automata, Petri nets, and especially my colleagues has developed this much more efficiently also for extended finite automata, where you have variables included with automata. So with that, let's see, I've got a question here. Why don't we join 4, 5, 6, 7? Why don't we join 3, 4, 5, 6, 7? Okay, when did this come? 54, it was some time ago, sorry. So I tried to answer that. I just would like to hear which question it was. Let me share the presentation again. Was it actually back to 3, 4, 5, 6, 7. Now it couldn't be here because this was quite late. This was not that either. Did you mean this, or the one who gave the question, please talk?
Who asked the question, participants? Please unmute yourself and tell.
Which slide?
Because I cannot see the question, so it was written to you. So,
Aha! It was just a personal question. Okay.
So who wrote the question? I don't know. Hello, who wrote the question? Please request you to unmute yourself.
Let's see, I can at least chat. Manbir Kaur.
Yeah.
Dr. Manbir Kaur.
Dr. Manbir Kaur.
Yeah.
Dr. Manbir, are you there?
Can you give me some feedback on which of the slides it was? 4, 5.
Yeah, she is.
Okay, it could not be this because it's a state 7, so it's not this either. So then I guess it could maybe be this one.
Manbirji, are you there? We cannot hear you. You're talking, it seems, but we cannot hear you. I don't know.
I think he has left.
No, she has unmuted herself.
Oh yeah, the DM, yeah, okay.
Yeah, this one, yeah, perhaps, yeah.
Okay.
What is the question? So she is speaking, or I don't know, but she's unmuted.
Yeah. Yeah, okay. I mean, I could just, let's see here, 3, 4. I just try to see, it, probably not this one either. At least, I mean, in this case, it's clear that 7, okay, now something comes. Okay, I understand now as states are P and Q. Okay, yeah. So so I think it looks like it's clear now. Did you ask about tomorrow's talk? Okay. Yeah. Okay. It's the problem is that we have this that I use the same account as Aparajita. So I read here about tomorrow's talk. Yeah. What will I talk about tomorrow? Is that the question? SM, Shraban Mohanty.
Yes. Yeah. Shraban is our co-coordinator of this course.
Oh yeah. Okay. So yes, I mean tomorrow I will try to give some applications. I don't have so much fantastic applications to tell you about, but I have some quite interesting ones I will mention, and if there is some time left, I will continue with some more material from this lesson. What will be tomorrow's schedule for GIAN? Okay, yeah. So the schedule for tomorrow, can you repeat that, Aparajita?
Yes. So tomorrow, let me just open. Please allow me to open. Give me a minute. So Who is asking? We have, in fact, shared with you all this updated one as well. So tomorrow you can see it's day 9, 15 to 16. We'll be having a short talk by Professor Bengt on research, his activities, research activities at his research group. So we'll start with 3 p.m. Indian Standard Time. And then from 16 to 17, it's a course, the lecture on applications of AI, learning planning, whatever he thinks. He was telling that he'll be talking about some applications. And then,
for instance, I have one interesting application on autonomous driving.
Okay, that's wonderful. And then 17, so from 5 p.m., we will have a small feedback and valedictory session. Feedback we'll be collecting through a Google form that we'll share with you. And then we also would like to have oral feedback from you. And then we invite you to the valedictory session as well. So it will be 3 to 5:30. And so Professor Bengt, Shravan was asking for the title of your talk for this particular session.
Yeah, so yes, I will give you a talk. And
as you told, yes.
I think it will be something like planning, learning, and sustainability or so. But I will look at that a bit more. Yes.
Sure. Sure.
Great.
Okay. So if there are no questions or there are questions, please let us know. So I request all of you to please put your videos on for a couple of seconds. Thank you, ma'am. So Manveerji, what you were saying, we were not able to hear. You were saying something, perhaps your mic was unmuted. So Shubhangi is asking me to make herself co-host. I'm sorry, Shubhangi, I thought I have already made you. So you are requested to please take a snapshot. You are keeping all the records. So I'm requesting you to please do that. Thank you. Thanks all the participants. Wish you a very good evening, relaxed evening. Have a nice dinner. And Professor has still a long time to go to take dinner, perhaps. Thank you so much, Professor Bengt. Yeah, and we meet tomorrow, the last day. Thank you.
Bye-bye.
Thank you so much. Bye-bye. Bye-bye, all of you.